Hello everyone from Math 2000, Linear Algebra. Professor Wenson here again with a video on your Zybooks, section 9.3, titled Orthogonal Bases. So let's just get into it. So in 2 and 3 dimensions, R2, R3, Euclidean space, orthogonal vectors are vectors that make a right angle. Now, there's a little caveat to this. This is when we're talking about the inner product being the dot product. You're going to see later in a second here that the definition of orthogonal depends on how the inner product of two vectors is defined. So the concept of orthogonality can be generalized to a relationship not only between vectors in an inner product space, but also between subspaces. For many applications, problems can be solved by choosing an appropriate basis for an inner product space. In many cases, the ideal basis is one in which all of the basis vectors are this word orthogonal. Fortunately, an orthogonal basis exists for every finite dimensional inner product space. Furthermore, a process exists by which any given basis can be used to construct an orthogonal basis. Now, what these words mean, orthogonal and orthogonal basis, we'll get into throughout this section. Alright, so you have the objectives here. So first part of this section is on, what does it mean for two vectors to be orthogonal? Right, so vectors u and v from some inner product space V, right, so a vector space with a properly defined inner product, are orthogonal if the inner product of u and v is 0. Okay. Now to add to this, vectors u and v, from an inner product space capital V, are called orthonormal if u and v are orthogonal and both of them are unit vectors. Now remember what it means from section 9.2, right? A vector is a unit vector if its norm is 1, right? Or if its magnitude is 1. So you see how the definition of orthogonal and orthonormal depends on how the inner product is defined, right? So whether or not vectors are orthogonal depends on the definition of the inner product. So you see the orthogonality of vectors depends on how the inner product is defined. Two vectors may be orthogonal under one inner product and not orthogonal under a different inner product. You may still be talking about the same space. So they give us an example here, which I'll actually write out. Let's get rid of the calculator. So we're in space R2. Right, we're talking R2 here, vectors, with two components that are real numbers. Now let's suppose I have a vector u with components, -3 and 6. And a vector v with components 2 and 1. And these both belong to R2. Now, case 1. What if the inner product of two vectors in R2 is defined to be just, the standard Euclidean inner product or the dot product? Well, in this case, the inner product of u and v that I was given up here would be, negative 3 times 2 plus 6 times 1, and that is 0. So because the inner product of these vectors is 0, we would then say that u and v are orthogonal under the dot product. Under the dot product, under this standard Euclidean inner product. And if you were to graph these as well, right? Here's the coordinate plane, and if I were to graph these vectors right in standard position in R2, starting from the origin here, u is negative 3, 6, so left 3, up 6, right? That motion. So there's u, right? Something like that. And vector v is 2, 1, right 2, up 1, right? And there's v. Right? And what you see is when you're talking about this standard inner product or the Euclidean inner product or the dot product in R2 or R3, orthogonal means perpendicular. They will meet at a right angle. But that's only when you're talking about the inner product being the dot product. If the inner product is the dot product, and you're in R2 or R3, orthogonal means the same thing as perpendicular. But under other dot products, orthogonal doesn't mean the same thing as perpendicular. All right, so if you have some other inner product, right, so their second example is this weighted Euclidean inner product. So where the inner product of u with v is defined as 4 times the product of the first components plus 5 times the product of the second components, right? This weighted Euclidean inner product. Well, let's check this. The inner product of our vectors here would be 4 times negative 3 times 2 plus 5 times 6 times 1. And this is negative 24 plus 30, which is 6. That is not 0. So under this inner product, these vectors are not orthogonal. So this leads me to say this statement: u and v are not orthogonal under this inner product. So it all depends on how the inner product is defined. Right? And under this inner product, if two vectors are orthogonal and you draw them, they're not going to be perpendicular. Right? They'll have an inner product of 0, but when you draw them, they don't meet at a right angle. So the only case in which orthogonal means the same as meeting at a right angle, meaning perpendicular, is when you're in R2 or R3 and your inner product is the dot product. That's it. All right. All other times, if the inner product is not the dot product, when I say orthogonal, I'm not going to say perpendicular. They don't always mean the same thing. So be careful with that. All right. So again, you can watch this animation here where they're doing the same stuff. All right. So for example, all right, I'll go over one of these. So I'll do the one with the polynomials here. These are actually part of the vector space of continuous functions, over the interval from -3 to 3. And they're asking, determine whether the given vectors are orthogonal, orthonormal, or neither. All right, so I'll write this out. Okay, so they told us it was in the first part of this activity that we have the integration inner product. Remember that on this space of continuous functions over the interval from -3 to 3. That means the inner product of two functions is the definite integral over that interval, from -3 to 3, of the product of those two functions. And you've seen this before. All right, so now the question is, I have two functions from this space, functions that are continuous, they're polynomials, they're continuous everywhere, P and Q, and then the question is, are P and Q orthogonal? I'll start with that. Are P and Q orthogonal under this inner product? Right? They may not be orthogonal under this inner product, but they might be orthogonal under some other inner product on this space. So again, you got to really pay attention. All right, so the answer to this is just take the inner product, right? What is the inner product of 1 plus x, p of x, with x minus x squared? All right, so this would be the definite integral from -3 to 3 of p of x times q of x, 1 plus x times x minus x squared. Then, with respect to x. Now this product here, if I were to multiply this out, you'd have, x minus x squared plus x squared, so the x squareds would be gone, and then minus x cubed. So this is just x minus x cubed with respect to x. And you may notice that this is an odd function here. The odd powered, all the terms are odd powered. And you may recall something from a calculus class that if you integrate from -a to a, right, over for an odd polynomial, that's 0. And you could finish it off if you want to do the antiderivative and plug in 3, plug in -3, and subtract. But this is 0. And since the inner product of these two functions is 0, then yes, P and Q are orthogonal. Under this inner product, right? Under the integration inner product. Now after here, I'm gonna stop writing under the inner product, right, just to save some time. But again, you got to know just because they say something's orthogonal, right? It all depends on how the inner product is defined. All right. So now that I know these functions are orthogonal, the next question was, are they orthonormal? Now, if the answer to this question was no, they can't possibly be orthonormal. All right. Orthonormal vectors are orthogonal, but also both of them are unit vectors. Right? So if the answer to this question were no, I'd stop. Don't even check if they're orthonormal. So question 2, but the answer was yes, right? So now the next question is, are P and Q orthonormal? So remember, orthonormal meant two things. They're orthogonal, which we already checked, so yes. And they're both unit vectors? So this is what we're checking now, right? Are they unit vectors? So we got to go back and remember the definition of norm from section 9.2. So I want to find the norm of P and the norm of Q and see, are they both 1, right? Are they both unit vectors? All right, so remember the definition of our norm from last section. It's the square root of the inner product of the vector with itself. All right. So, off to the side here, I'm going to take this, inner product of P with itself. This would be the integral from -3 to 3 of P of x, right, which is 1 plus x times P of x again, so P of x squared, right, with respect to x. Okay, since this is a simple linear here, I could, this is equal to 1 plus x cubed over 3. All right, the derivative of this would be that. Then from -3 to 3. And you plug in 3 here, you'd get 4 cubed, which is 64 thirds. And then subtract the value at -3, and 1 plus -3 would be -2. Cubed would be -8 thirds, so it would be plus 8 thirds. And we're getting 21 and, this is 21 and 1/3 plus 2 and 2/3. So this is 23, 24. So the norm of P, right, the norm, the magnitude of this polynomial, this function, is the square root of 24, which is not 1. So that tells me that P, right, P of x equals 1 plus x, is not a unit vector, right, under this inner product. But I'm going to stop writing that. Right? It's not a unit vector in this vector space, under this inner product. And if that's the case, I don't need to check Q. I don't need to check Q, because in order for a pair of vectors to be orthonormal, they have to be first orthogonal, their inner product is 0, and they both have to be unit vectors. And so if one of them is not a unit vector, then the answer is no, right? So these vectors are orthogonal, but they're not orthonormal, because they're not both unit vectors. So this option here. All right. Okay. And you can see that also Q doesn't have a norm of 1 as well. You could do the same thing for Q. They're saying here neither function has a norm of 1. So you test that out. All right, then you can do this for 2, right? You have these matrices under the Frobenius inner product, which hopefully by now you know and have heard of. All right. So now we're going to extend this. So far we've been looking at just pairs of vectors, right? Is this pair of vectors orthogonal? And if it's orthogonal, are they orthonormal? Are they both unit vectors? We're going to extend this now to sets of vectors with more than just two vectors. So an orthogonal set of vectors, say called S, is a set in which each vector is orthogonal to every other vector, right? Every other one. No vector is orthogonal to itself, except the 0 vector, I guess you could say, is orthogonal with itself. But no vector is orthogonal, no non-zero vector is orthogonal to itself. So this is a set in which every vector is orthogonal to every other vector. So symbolically, if vectors v and w belong to an orthogonal set called S, then their inner product will be 0, right? That's what it means for vectors to be orthogonal. And this is whenever v is not w, right? Whenever they're not the same vector. So you have to look at, and this can be a bit tedious, if you're asked, is this set of vectors orthogonal, you have to look at every pair of vectors and see if every pair of vectors is orthogonal. And if that's the case, then it's an orthogonal set. All right. An orthonormal set is an orthogonal set of unit vectors. All right, so kind of, again, a natural extension of a pair of vectors being orthonormal. All right, so an orthonormal set means every pair of vectors is orthogonal, and every vector in the set is a unit vector, has a norm of 1. And then here's something nice and pretty. It's pretty about orthogonal sets. The Pythagorean theorem for orthogonal sets. If you have an orthogonal set of vectors, so say u1 through uk here make up an orthogonal set. That means u1 and u2 are orthogonal, u1 and u3 are orthogonal, u1 all the way up to uk are orthogonal. Same thing with u2 and u3, u2 and u4, u2 and u5, etc. Every pair of vectors is orthogonal. Then the sum of all the vectors, their norm squared, right, which would just be the inner product of the sum of the vectors with itself, is equal to the norm of each vector squared separately added up. Right, and here's a proof down here in the case when you just have two orthogonal vectors. Right? And again, they tell you how it could be extended to k orthogonal vectors pretty easily. All right, so I'll let you read this example here, and I'll get into one of the activities. So here's a set of vectors from R3, and you're asked, is this set of 3 vectors orthogonal, orthonormal, or neither? All right, with respect to the standard inner product. Now remember, the standard inner product or the Euclidean inner product is the dot product. Right. So do you see how they take every pair of vectors here and check that the dot product is 0? Right, you got to do it for every pair of vectors. And then after they say, oh look, every pair of vectors is orthogonal, now the question is every vector a unit vector? So then they find the norm. Remember the square root of the inner product of a vector with itself. They find the norm of every vector is 1. Hey, look. So this is an orthogonal set, and since every vector is a unit vector, it's also called an orthonormal set. So every orthonormal set is an orthogonal set, but not the other way around, right? You can have orthogonal sets that aren't orthonormal. All right, so let's look at an example here. Lots of square roots and stuff. All right, I'll let you do number 1. It's another, it's a weighted Euclidean inner product. I'll look at number 2. So I have a set of three matrices, and we're under the Frobenius inner product, which again is like you've seen this before. It's like the dot product for matrices. You just multiply corresponding entries and add up those products. All right, so I'll write this out and we'll take a look. Is this set of vectors, right? This set of matrices in R2 by 2, an orthogonal set? And if it is an orthogonal set, then we'll ask the question, is it an orthonormal set? Okay, so here's this set of 3 matrices from R2 by 2, right? We got the Frobenius inner product. And we're asked, I called it set S. We're asked, is set S So is S an orthogonal set? So remember, an orthogonal set of vectors, every pair of different vectors has to be orthogonal. So I need to check all of the following. Now there are 3 vectors, and how many ways can you choose 2 different vectors out of 3? That's 3 choose 2. Those of you that know combinations, that's just 3. There's only 3 ways to do this. So one is I'll check the inner product of A with B. So the inner product of A with B, and doing Frobenius here, well, this is A, this is B, that'd be 0 plus then a negative 2 over the square root of 210. I'm going to multiply those components, plus positive 2 over the square root of 210, and then plus 0. And this is equal to 0. So far so good. Right? So A and B are orthogonal under the Frobenius inner product. But that's not all, right? Let's do A and C. Right, so A with C, Frobenius, this would be 6 over whatever the square root of 42 times 37 is. I'll just put 42 times 37 down here, whatever that is. Plus 0 plus 0 and then plus and then negative 6 over the square root of 42 times 37, and these would cancel and you have 0 again. Great. So A and B are orthogonal under the Frobenius inner product. A and C are orthogonal, but there's still one more pair, right? B and C. So I do the Frobenius product here. We have 0 plus 0 plus 0, and hey, look at this. 0, oh my goodness. It's all 0, so yes. S is an orthogonal set. Every pair of vectors, right? Every pair of matrices has an inner product of 0. Every pair of vectors is orthogonal. All right, so now that the answer to this one was yes, we can ask the second question. Is S an orthonormal set? So again, to be orthonormal, you have to be an orthogonal set, which we just showed, and every vector, right, so all 3 of them, have to be unit vectors. So let's look at the norms of each of these. So the norm of A. Remember the definition of norm here, we're doing the square root of the inner product of A with itself. Alright, so this will be the square root. Let's do it all right here now. Alright, so inner product of A with A would just be 36 over 42. Right, multiplying that by itself, plus 1 over 42 plus 4 over 42 plus 1 over 42 again. And 30, these all have the same denominator. Can you see the sum of the numerators is 42. This is 42 out of 42, which is 1, and the square root of 1 is 1. So matrix A is a unit vector under the Frobenius inner product. So I keep going. Right. How about matrix B? So same deal. Take the square root of the inner product of B with itself. So this is the square root of 0 plus 4/5 plus 1/5 plus 0, which is 1. All right, you have the 5/5 in here. So B is a unit vector under the Frobenius inner product. And finally, the norm of C, right, the square root of the inner product of C with itself. So the square root of 1/37th plus 0 plus 0 plus 36/37ths, which is again 1. So every single vector, A, B, and C, are all unit vectors under this Frobenius inner product, and we already saw that it was orthogonal. All right, so it is an orthogonal set where every vector is a unit vector, so it is also considered an orthonormal set. So orthonormal, yes. Right. Last to check. And this is only a set with 3 vectors. Right? If you had a set with 5 vectors, for example, to see if it's an orthogonal set, you'd have to do 5 choose 2 inner products. Look at every pair. 5 choose 2 is 10. You'd have to do, check 10 different pairs to see if it's an orthogonal set. And then if it was, then you're going to check to see if all 5 of them are unit vectors. Right? So the larger the set, the longer this takes. All right. Now here's an amazing thing. All right. If we know that a set is orthogonal, if we know a set of vectors is orthogonal, non-zero vectors, then that set of vectors will also be linearly independent. So if a set S of non-zero vectors is orthogonal, then the set is also linearly independent. Furthermore, that set S would be called an orthogonal basis for the subspace spanned by S. And again, you can read through the proof here. I'm not going to go over the proof with you. Just understand that orthogonal sets are very nice. They're very nice. Orthogonal sets of non-zero vectors, of course. All right, so they mentioned orthogonal basis. It's just a basis for a vector space that's an orthogonal set. All right, so you remember what a basis was, I hope. So an orthogonal basis for a vector space V is just a basis that is also an orthogonal set. And in a similar fashion, an orthonormal basis for a vector space is just a basis that is an orthonormal set. So, simple enough. An orthonormal basis can be constructed from an orthogonal basis by dividing each basis vector by the vector's norm. All right, remember what happens when you take a vector and divide it by its length back in Euclidean space? You got a unit vector. That was called normalize. That's called normalizing a vector, changing a vector into a unit vector that points in the same direction. So that's all they're saying here is if you have a set that's orthogonal and you'd like to make it orthonormal, just divide every vector by its norm and you'll have a set of unit vectors. All right, so I'll do an example here. All right, well actually I'll let you read these. Let's do this one. All right, so I'll do number 1. All right, so if S is this set of 3 vectors here from R3, say that they're telling us it's an orthogonal basis, right? So it's a basis for R3, right? That means it spans R3 and they're linearly independent. And it's also an orthogonal basis, so every pair of vectors in here is orthogonal. Now, if they don't mention an inner product, let's just assume the dot product. Okay, if they don't mention an inner product, we can assume the standard inner product or the dot product here. So let me show you how I would change this orthogonal basis to a set that's orthonormal, an orthonormal basis for R3. Okay, so like I was saying, they give us this set here that is an orthogonal basis for R3. And I'll call these vectors v1, v2, and v3. Now, what I would like to do now is construct from this orthogonal basis an orthonormal basis for R3. And again, it's very simple. If you already have an orthogonal set, construct an orthonormal basis for R3 under the standard inner product, right, under the dot product. All right, well, again, it's very simple. Just if you know a set is already orthogonal, to make every vector into a unit vector, you just need to divide, or multiply by the reciprocal of each of these vectors' norms. Okay, so let's find the norm of vector, v1. So again, this would just be the square root of, the dot product, right? The inner product here is the dot product. The dot product of v1 with itself. So 1 squared plus 2 squared plus 1 squared. This is 1 plus 4 plus 1. This is square root of 6, right? Which is definitely not 1, right? So this is not a unit vector. So to make a unit vector out of this, I just take 1 over the square root of 6 and multiply it by v1. Right? And this will have a norm of 1, right? You could check that out by the homogeneity property. So this would be, 1 over the square root of 6, 2 over the square root of 6, 1 over the square root of 6. This vector is a unit vector. Right? And what I just did, by taking a vector and multiplying it by the reciprocal of its norm, that's called normalizing a vector, right? Normalizing. So let's just normalize these other two vectors now. So I'm going to find the norm. Let's find the norm of vector 2. So this would be this, again, the square root of, it's the inner product here is the dot product. So the dot product of this vector with itself. So, 2 squared plus 0 squared plus negative 2 squared. Right. So it's the square root of 8, which is just, 2 root 2 if you want, right? So another unit vector I can create is 1 over, 2 root 2, the reciprocal of the norm times v2. And this would be, 1 over the square root of 2, right, because the 2's would cancel. Right, you'd have the 2 here, the 2 in the denominator. So just 1 over the square root of 2, 0, and then negative 1 over the square root of 2. This is also a unit vector. Right, I just normalized v2. Right, and finally, take the norm of v3. So again, it's the square root of the inner product of that vector with itself, which is, the dot product again. So that's the square of, 16 plus 16 plus 16, right? Negative 4 squared plus 4 squared plus negative 4 squared. It's the square root of 48, which you see that's 16 times 3, so this is 4 root 3, right? 4 root 3. So if I multiply, v3 by the reciprocal of its norm, right, 1 over 4 root 3 times v3 would be the following. Now you see how the 4's would cancel in all these? You just have negative 1 over root 3, positive 1 over root 3, and negative 1 over root 3. And there you go. This vector here would be a unit vector. And again, you can check all this. Make sure all these vectors I'm saying are unit vectors actually have a norm of 1. And then putting all these together, we get our normalized set. All right, so this set here, which they're calling, S prime, because it's like coming from S, but it's different from S. has just the normalized vectors from this orthogonal set. All right, so it was, again, 1 over the square root of 6, 2 over the square root of 6, 1 over the square root of 6, and 1 over root 2, zero, negative 1 over root 2. And finally, that last one, negative 1 over root 3, positive 1 over root 3, negative 1 over root 3. Okay, this set of vectors forms an orthonormal basis. This would be an orthonormal basis for R3 under the standard inner product, right, under the dot product. And again, what this means is that if you take any vector in R3, it can be written as a linear combination of these three vectors. And since this is an orthogonal set, these vectors are independent. So we have a basis for R3 of vectors that are also form an orthonormal set, all unit vectors that are orthogonal. All right. So they're saying here, yes, is this an orthonormal basis? No, right? I needed the square roots under these, so this is false. This is the set I got after again taking the orthogonal set and normalizing, just dividing every vector by its norm. So you would do the same here, right? Find the norm. They're telling you this set of polynomials here is an orthogonal basis for P2 under the integration inner product. This integration inner product here. And if you want an orthonormal basis, you would just go and find the norm of these three vectors and divide each vector by its norm to get an orthonormal basis for P2 under the integration inner product. Okay. All right, so now this last part on something called Gram-Schmidt orthogonalization is a process. It's a procedure to take any basis for a vector space or an inner product space, right, with a defined inner product. You can take any basis for an inner product space and construct from it an orthogonal basis. And then therefore you can also construct an orthonormal basis, because once you've constructed an orthogonal basis, like S up here, then you just normalize each vector and you'll get an orthonormal basis. Right? Yeah, so this goes over the procedure. Now I have another video in your Canvas page where I go through the Gram-Schmidt orthogonalization process in a little more depth and kind of show you the motivation for this formula. I'm not going to do that here. All right, if you want, you can watch that other video of mine. I'm just going to go through the procedure and show you an example, one example, because these, if you want to see more examples, go to my other video on the Gram-Schmidt orthogonalization process. Right, so here it is. So as shown earlier, right, orthogonal and orthonormal bases can be very useful because they're independent and whatnot. Conveniently, any basis can be changed into an orthogonal basis by means of this thing called the Gram-Schmidt process. All right, so here it is. Suppose U1, U2, all the way up to say UM right, and this set of M vectors here is a linearly independent list of vectors in some space W. Now, again, we're starting with really any set of independent vectors from W. A set of any base, we're starting with any basis of W. Now here's how you construct an orthogonal basis from this original basis. So you're going to start with a vector v1. All right, now just simply have v1 be the first vector in your original basis. All right. So the way this is constructed really depends on, what order you put your original basis vectors in. If you put these in a different order, you'll construct a different orthogonal basis. So let v1 be the first vector from your basis, u1. All right, then for all the other these other v vectors you're constructing, v2 through vm, say vn is going to be un. All right, so you pick the same vector, the corresponding vector from the original basis, and then from that you subtract the projection. You subtract the projection of this un onto all the previous v vectors that you created. Remember the projection, these are the formula for a projection of vector un onto v1 would be the inner product of un and v1 divided by the inner product of v1 and v1 times v1. And then this is the projection, the vector projection of un onto v2. This is the projection of un onto v sub n minus 1, right, the previous v. And this set of vectors v will be an orthogonal list of vectors. Right. And if you want to make an orthonormal, just take this orthogonal list and normalize, right? Just to take every vector in this list, find their norms, divide everything by their norms, right? And you'll have an orthonormal basis. All right, so that's a lot of letters, a lot of symbols. Let me just show you an actual example of this. Now I'll let you read this first one. All right, so here, this set of three vectors is a basis for a subspace of R3. Right. So it's a basis for some vector space. You're asked to use the Gram-Schmidt process to orthogonalize the basis. So transform, from this basis, construct a different set of three vectors that also forms a basis, but it's a set of three vectors that's orthogonal. Right. And this would be under the dot product here. Again, they didn't mention any specific inner product. So if they don't mention a specific inner product, you're using the dot product. Right, so again, please read this example on your own, and then they normalize at the end. Right. All right, so I'm going to do the Gram-Schmidt process with this set of four vectors. So here I have a set of four vectors that form a basis for R4. And again, the dot product here is the inner product. They didn't mention any particular inner product, so I'm going to be using the dot product. Now this set of vectors is not orthogonal, right, under the dot product. Just take, for example, the first vector and fourth vector. Their dot product would be 0 plus 0 plus 0 plus negative 4. So the first and fourth vector, right, they have a dot product, an inner product of negative 4, not 0. So this is not an orthogonal set. But what I am going to do is I can take any set and construct an orthogonal set from it. I can take any basis of a vector space and construct an orthogonal basis using this Gram-Schmidt process. All right. So hopefully you can follow me here. And again, like I said, I have another video in the Canvas page for this section where I do other examples, more examples. So hopefully you can watch those too if this one gets you stuck. So here we have this set of, again, 4 vectors that, do form a basis for our 4. But, S, this set is not an orthogonal set. I called it S, they didn't call it S. But this is not an orthogonal set. Oops. Orthogonal, that's a T, if you can tell. This is not an orthogonal set under the dot product, right? Under the standard inner product. The dot product, right? So, what I would like to do, again, is from this set, construct an orthogonal basis, right? A new set of 4 vectors that is not only a basis for R4, but is also orthogonal under the dot product. So we're going to construct an orthogonal set, an orthogonal basis for R4. From set S, and using what's called the Graham-Schmidt process. Right. And this other set I'll call, S prime, and it'll have vectors. I called these vectors from S, the original basis, U1 through U4. We'll call these vectors in S prime V1 through V4. All right, so I'll start the process on this next page. All right. So again, V1 through V4 in S prime here. So V1, and the very first vector in my new set, this orthogonal set I'm trying to construct. Very easy, just V1 is U1. Right, so the first vector from my original basis. So 1, 0, 0, 2. Okay, and then here's what that formula was saying after. V2. Okay, V2 is going to be U2, okay, the second vector from the original basis, minus, now I like writing this out, the vector projection, remember this projection symbol, the projection of U2 onto the first vector V1, the first vector in this new set I created. Now the formula for a vector projection, this is U2 minus, and then the projection of U2 onto V1, you have the dot product, or the inner product of U2 with V1 divided by the inner product of V1 with itself times V1. All right, and I'll write out what all this is. Okay, so U2, well, U2 is, this vector here, 0, -1, 2, 0. Minus, and then the dot product of U2 and V1. U2 and V1, or just these first 2 vectors really, would be, again, it's dot product for the inner product. So 0 plus 0 plus 0 plus 0. Hey. So it doesn't matter what the other stuff is. Okay, it doesn't matter. Well, I guess I should, the denominator, remember the inner product of a vector with itself, as long as it's not the 0 vector, is not going to be 0, so I don't have to worry about dividing by 0 here. So this is gone. This second term is actually gone, because that numerator is 0 in that scalar. So that's all 0. So V2 ends up being U2. Great. For this example, doesn't always happen. Okay, doesn't always happen. It's only because these first 2 vectors actually are orthogonal under the dot product, right? So V2 is the same as U2. So 0, -1, 2, 0. All right, then again, to continue this just keeps getting extended the more vectors there are. So if I want the vector V3, let me Just get rid of this now. So let's remember, u1 is the same as v1, and from our last line, u2 is the same as v2. All right, so now for the third vector, v3. Again, I just take u3, take the third vector from my original basis, and then I'm taking away now two projections. I take away the projection, the vector projection of u3 onto v1, and also onto v2, all the previous v vectors, all the previous new vectors that I've constructed, minus the projection, the vector projection of u3 onto v2. All right. And again, the formulas for these, this would be u3 minus, and then the projection of u3 onto v1. Sorry, I paused it for some barking and stuff. All right, so the projection of vector u3 onto v1, again, would have this formula. You have vector u3 inner product with v1 divided by the inner product of v1 with v1 times v1, minus the projection of u3 onto v2, would have a very similar formula. Just instead of v1s, you have v2s. So the inner product of u3 with v2 divided by the inner product of v2 with v2 times v2. All right, so let me do all this. And just remember that v1 was just u1, and v2, after running through the formula, ended up just being u2. Okay. All right, so u3 is this vector here, right, with -2, 0, 1, 0, minus. Now u3, now again, the inner product here is the dot product, so I'm doing u3 with v1. So that'd be -2 plus 0 plus 0 plus 0. So -2 in the numerator. And then the denominator is the inner product of v1 with v1, which is u1. So 1 plus 4 is 5. Then this is multiplied by vector v1, which is u1, 1, 0, 0, 2. And then from this we're also subtracting, well, this will be adding because I have minus -2/5 here. But then minus, then here, this projection, u3 with v2 is just u3 with u2, right? v2 ended up being u2, so the dot product is 0, 0, 2, and 0. And the inner product of v2 with itself, or u2 with itself in this case, is again 5. Pardon me. Yeah. Right, sorry about that again. Somebody at my door. All right, so we had the u3 inner product with v2, 2 is, and then the inner product of v2 with itself was 5. Then times v2. Now remember, v2 was u2. So from my earlier page. All right, now combining all this stuff, we get a new vector. So remember, these minuses will basically be plus now. Minus, minus. All right, so the first component, you have -2 plus 2/5, and then minus 0. So -10/5 plus 2/5 be -8/5 for the first component. And then second component, 0 plus 0, and plus 2/5, right? So 2/5 for the second component. Then the third component's 1 plus 0, and then minus 4/5, right, would be 1/5. Right? And then finally, 0 plus 4/5 minus 0. Right, so here, this vector is v3. All right, v3. Now, something I'm noticing about v3 is that all of them have a common scalar factor of 1/5. So I'll have v3 I mean, you can use this, no problem. But just to make some calculations maybe a little easier later, I'm going to pull the fifth out. I'm going to pull that scalar out, and then times the vector -8, 2, 1, and 4. Okay, there's V3. Alright, so now I've got V1, V2, V3. Last one, to finish off my orthogonal set, V4. Alright, so V4 is going to be, U4. So I'm taking the fourth vector, right, from my original basis, this 0, 0, -1, -2. And then I'm just going to subtract now there were three previous V vectors. I'm going to subtract the projection of U4 onto those three. So minus the projection of vector U4 onto V1 minus the projection of U4 onto V2 minus the projection of U4 onto V3, right? And again, the further along you go, the larger the basis is, the longer this expression gets, the more and more vectors you construct. All right. So U4, again, was this fourth vector. I'll just do this here. Was the fourth vector from our original basis. So 0, 0, -1, -2. Minus. Remember the projection. First, there's a fraction. The numerator is the inner product, or the dot product in this case, of U4 with V1. And remember, V1 was the same as U1. So the dot product of these two vectors. So we have 0 plus 0 plus 0 minus 4 divided by, and then we saw the dot product of V1 with itself, or U1 with itself, same thing, would be 5. Then times V1, right? Times which was the same as U1, 1, 0, 0, 2. Okay. Minus. Then the projection of U4, right, onto V2, which again earlier we saw V2 was the same as U2. Not always happening, but in this case it worked out that way because the first two vectors are orthogonal. Alright, so U4 dot V2 would be 0, 0, -2, and 0, so -2. And the dot product of V2 with itself, U2 with itself, is again 5. And then times V2, which was U2, 0, -1, 2, 0. All right. Now I need V3 minus the projection of U4, which is this vector here, and V3, right, on the projection of U4 onto V3. And this was V3 from the last page. Right, so I'm projecting this onto this. Okay, so the numerator, right, the dot product of U4 and V3. That's why I pulled the scalar out, because it'll make it easier, I think. Do the dot product of these vectors, then times 1/5. Remember, the dot product has a homogeneity property. So 0, 0, -1 plus -8 is -9, right? But then times 1/5. So -9/5 in the numerator there, right? We get a little complex fraction going. And then the denominator is, the dot product of V3 with itself. So the dot product of this with itself, so I'd have 1/5 twice, I'd have 1/25. You have 64 plus 4 is 68. I'm just squaring all these. 64 plus 4 is 68, plus 1 is 69, and plus 16 would be 85. And then we have times, 1/25. So 85/25 is the dot product of V3 with itself. And then times V3, right? Times V3, so times 1/5, another fraction here, times the vector -8, 2, 1, 4. All right, now I'm going to clean this up a bit. So we have 0, 0, -1, -2. Then, plus 4/5 times 1, 0, 0, 2, plus 2/5 times 0, -1, 2, 0. And then this, you see that multiplies multiply the numerator by 1, I'll have -9/5. If I multiply the denominator by 5, that'll make this into 85/5. And then I can multiply the top and bottom by 5 and cancel the 5s. So those cancel and those cancel. So this is just plus 9/85. Right? Plus 9/85 times this vector -8, 2, 1, 4. Okay, and you see they're going to have a common denominator of 85. I'm putting all this together, and I'm looking at this. I'm kind of cheating. I'm looking at the final answer here. But if you were to put all this together, right, like all the first components, let's say, 0 plus 4/5 plus 0, and then minus 72/85. Well, 4/5, if I want it in terms of 80/5, I need to multiply by 17. 4 times 17 is 68, right? And 68/85 minus 72/85 would be, -4/85. All right, -4/85. Or I could just do something here where I combine, get a common denominator. Like this is, like I said, this is 68/85 plus 9/85, and pull out the 1/85 and then use 60. It'll take a while for that too. But if I go through the second components, I'll get -16/85. Go through the third components, get -8/85, and go through all the fourth components, get 2/85. And there we go. All right. And if you want, you can pull the 1/85 out of this, right? So I'll do that. This is 1/85. Well, in fact, each of them has 2/85 in common. Pull out 2/85 times the vector, -2 and -8, -4, and 1. And there's V4. So after all that, right, you see how tedious this can be, especially with a larger set of vectors. But after all that, we have constructed this orthogonal basis. For R4. And I was calling it S prime. And it had, V1, which was the same as U1. So the vector 1, 0, 0, 2. V2 ended up being the same as U2. 0, -1, 2, 0. V3 ended up being this vector. So you could put the 1/5 in again if you want. I'm just leaving it outside. 1/5 times the vector -8, 2, 1, 4. And finally, V4 ended up being this thing, 2/85 times the vector -2, -4, -8, -4, and 1. All right. This is an orthogonal basis for R4. So it's a basis for R4, meaning every vector in R4 can be written as a linear combination of these, and they're independent. And it's also an orthogonal set. Right? You can check it out by taking the dot product of any two of these. Well, I'll just do it real quick here. Dot product of these two is 0. How about these two? Now I just do the dot product of these vectors and times 1/5. So you see negative 8 plus 0 plus 0 plus 8, that's 0. These are orthogonal. These two, negative 2 plus 0 plus 0 minus 2, these are orthogonal. And then how about these two? 0 minus 2 plus 0, these are orthogonal. How about these two? 16 minus 16 minus 4 plus 4, these are orthogonal. And there's 6 pairs I'd need to check, but every pair of vectors in here has a dot product of 0. Every pair of vectors now are orthogonal. All right. Now, if you wanted to take this and then construct what an orthonormal basis, if they said to construct an orthonormal basis, well, just normalize each vector. Once you have an orthogonal basis, just normalize each vector, right? So I'm not doing that. That would take too long. But I find the norm of this vector. Well, I guess it wouldn't take that long, but the norm of this vector, right, would be the square root of 5. I divide it by the square root of 5. Same thing for this vector. The norm of this vector is the square root of 5 divided by the square root of 5. The norm of this vector, I'd have to find, it'd be a big square root and all that. Remember, you take the dot product of the vector with itself and then take the square root. And then divide by that norm, and then take the norm of this vector and divide it by its norm, and you'll have a new set of 4 vectors. Maybe call it S double prime or something, because it came from S prime, and it'll be on an orthonormal basis. Okay, so again, you can see how long. Now, when there are only 2 or 3 vectors, it doesn't take that long. 4 or more, like this example here, it could take a while. All right, now they're asking you to do the same for these activities, which again I would leave to you. But here are 2 matrices. Now these form a basis for a subspace of R2 by 2, right? They don't form a basis for R2 by 2. R2 by 2 is dimension 4. So these 2 matrices, right? These form a basis for a 2-dimensional subspace of R2 by 2. And then, these are under the Frobenius inner product. These are not orthogonal, right? The Frobenius inner product would be like 26, not 0. So I take this basis for a 2-dimensional subspace of R2 by 2, and I can construct an orthogonal, and then therefore an orthonormal basis for that 2-dimensional subspace. So again, you see V1 just have be U1, and then V2 is going to be U2 minus the projection of U2 onto V1, which involves the inner product of U2 with V1 divided by the inner product of V1 with V1 times V1, right? And you do all that. All right, then you'll have V1, you'll have V2. These two here, oh, this might be V2, I don't know, it says true or false. But you'll have a V1, you'll have a V2, which will be an orthogonal basis for this 2-dimensional subspace. And then to find this orthonormal basis, you would find the norm of each vector and divide each vector by that norm, right? Normalize. Like I said, I'm only doing the one example. They take a while. You can watch, again, my other video. I have another video with other examples if you want to see them. And here's a challenge activity where, given an original basis, asked to construct an orthogonal basis, using the Graham-Schmidt process. Same thing for the second level. Now the nice thing is, they give you V1 and V2, you just have to find the third one. Right? What are A, B, and C? What are the components of the third one? Rounded to 2 decimal places, see. See their examples, 1.23, 1.23, so probably rounded to 2 decimal places, these components. Same thing here. Same thing here. You have to fill in A and B and C and D. So here you have to find V2 and V3 and then say what A, B, C, and D are. And then here the inner product is the integration inner product. But it's the same procedure, just with polynomials in this inner product, or with matrices in the Frobenius inner product, or whatever, right? The procedure doesn't change. It's the vectors that change, right? They might be polynomials, they might be actual vectors from Euclidean space, they might be functions, matrices, and the inner products that change, right? But the procedure, the formula, the way you do it is the same every single time. And then you have your additional exercises. Okay, so again, some of these are assigned, some are not. I would still recommend looking at all of them and practicing all of them, just to get more exposure to the material, more practice. And you also have the solutions to fall back on, if you want to check yourself. But please, look at the solutions after you've worked on them. Right? Work on the problem first, and then check the solution out to see if you did it all right. You're not going to learn anything if you're just copying the solutions down straight away and not trying the problems. So I'm hoping that this was a good introduction, at least, to some of this stuff. Like I said, I have other videos in the Canvas page that have more examples, maybe take it a bit further. And hopefully this is a video that's a decent enough guide for you for section 9.3. And if you have any questions, of course, send me a message and I'll get back to you as soon as possible. And thank you very much for watching.